All right, we're going to go through what I think will be the last couple problems on our readiness review assessment. Okay, so in number 29, we have a function given to us as a set of ordered pairs. Well, I should say a set of ordered pairs given to us, and then we have to say, well, which one should be removed so that it is a function. And one of the options is none of the above. And so this question is, of course, just asking us to, make sure we're okay with the definition of the function. Definition of function: every input goes to exactly one output. So here I see 4 going to 3, 5 also going to 3. That's okay. You can have two different inputs going to the same output. Think about a parabola. When you graph a parabola, an upward-facing vertical parabola, you have two different inputs that have the same output. Two different x values go to the same y value, and that's a function. Passes the vertical line test. What's not okay is if one input goes to two different outputs. And so as we go to the next one, we see, okay, 4 now going to 2, but wait a second, you said that 4 goes to 3. So I can't have both of those. It doesn't matter which one I get rid of, I just can't have them both. But the only one they give me the option to get rid of is the first one, 4, 3. They don't give me the choice of getting rid of the 4, 2. So, yeah, it's got to be that first one. Okay, another kind of function question, which one has to be removed from the domain? We know, hopefully from Math 4 pre-calc, that there's only 3 reasons why something would not be in the domain. A value would not be in the domain of a function if it makes the denominator of the function 0. We know that dividing by 0 is undefined. If it results in a negative under an even root, a second root, a fourth root, a sixth root, etc. Or if it makes what's inside the logarithm either 0 or negative. Well, there's no roots, there's no logs, so the only thing I have to worry about here is what makes the denominator 0. And that's going to be easiest to see if I factor that. That factors as x minus 3x plus 2. So I can see there's two values that would make that denominator 0. 3, not part of the domain, and negative 2, not part of the domain. We're looking for the values that are not part of the domain. Notice that we could also factor the numerator. The numerator would factor as x minus 3 and x plus 1. Now, sometimes people see this and we think, oh, well, the minus 3's cancel out, so then that is part of my domain. But no, it's not. Thinking back to the first several problems of this review activity, this would result in a hole. Well, if there's a hole, that's not a value in the function. And we talked in my explanation about how if you were to graph the original function where you keep the x minus 3's and the new simplified function, they would be almost the same if you just graphed this squiggly part, x plus 1 over x plus 2. The two graphs would be indistinguishable if you just looked at them. But if you actually checked, you would see that the original function would have a hole at x equals 3, and the new one would not. So the x equals 3 is not part of the domain of the original function f because there's a hole there. Also, the x plus 1 doesn't matter. That creates an x-intercept, but that's fine. That's part of the domain. For the domain, we only care about what's making the denominator 0, or if we have roots or logs, then there's those other things to consider as well. And hey, look at that, number 31 has a log. But in this case, it's not about domain, it's just about evaluating the function. So they give us two separate functions, f and g, and they want f of g of 3. There's two ways to do this. One, you could take g of x and actually plug it in here and rewrite your simplified composition function f of g of x. Or you can simply find g of 3. G of 3 is 9, and then plug that into f of x. So then I want f of 9. My 3 looks bad there. because I want f of g of 3, and g of 3 is 9. So I can replace this g of 3 here with a 9, because g of 3 is 9. And then if I plug that into f, it's log base 3 of 9, which that expression means 3 to what power is 9? 3 to the second power is 9. Okay, going on. So now we're thinking about inverse functions. And the definition of an inverse is that you switch the input and the output. So the way that we usually do this algebraically is we say, well, I like to think about x as my input, y as my output. So if I switch them, I'm just going to switch which one is x and which one is y. So I'm going to say x equals 3y plus 4, and you solve that. You're going to get x minus 4 over 3 is equal to y, which is f inverse of x. I always like to point out here that the inverse can be thought of as undoing the original function. So if you look at what we did in the original function, it says, okay, take some input, multiply it by 3, then add 4 to it. The inverse does the opposite in the opposite order. First multiply 3, then add 4. So this says, okay, first subtract 4, that's the opposite of adding 4, then divide by 3, that's the opposite of multiplying by 3, and do it in the opposite order. First subtract, then divide, versus first multiply, then add. Nice to kind of point that out, I think. 33 is just distance formula here. So just set that up, hopefully fairly straightforward. Distance formula is definitely something we use. Kind of could have lumped this one in our geometry review from a moment ago. So with distance formula, it's just the change in x. So negative 3 minus 4 squared plus 5 minus negative 1 squared. And remember, what you're really doing here is you're making a right triangle. So if I were to plot these points here, negative 3, I'll just say 1, 2, 3, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, negative 1. And when I do that 3 minus negative 4, I'm finding the length of this leg of a right triangle. And the 5 minus negative 1, I'm finding this length. And I square those and add them because it's a squared plus b squared equals c squared. It's just Pythagorean theorem. Simplify that, and we get, I believe, about 9.2 here. Zeros of the function, this is really just a vocab question. Do you remember what it means to be a zero? Zero, x-intercept, roots, all interchangeable terms. So you're just setting this function equal to 0, why it's called a 0. What are the x values that make the output 0? And solving. And you can solve this by trying to factor it, by quadratic formula, completing the square, whatever method you choose. I think I factored it, and I got 3x. I know the first factor's got to be a 3x and an x in each of the, or the first term in each factor has to be 3x and x. And then it's just a matter of, okay, what could this be? Well, I could do 2 times 2, 4 times 1. One of them's got to be negative. And the way that will work out is if this one is 4, because then it gives me a negative 12, and then this one is positive 1. So I'm going to get negative 1/3, drag that over, and I'm going to get positive 4, drag that over. Okay. 2 more, almost there. A lot of videos here. This kind of builds off of that idea. We're just solving a quadratic, but this one is super important because it's an inequality. And when we have this inequality, the first thing we want to do, just like with solving a quadratic equation, is we want the one side to be equal to 0. So I'm going to make this 2x squared plus x minus 6 is greater than 0. Then I solve like normal. And again, this factors, so that's friendly. I'm going to get 2x and x. With the 6, I've got a couple choices. One has to be positive, one has to be negative. So if I think this through, if I make this a plus 2 and this a minus 3, when I multiply that out, it's going to be a positive 4x and a negative 3x, which will give me just the positive 1 when I add them, positive 1x. Now, a lot of people, what we do is we just make this 2x minus 3 is greater than 0, x plus 2 is greater than 0, but no, that's not right. Do not do that. This is where we have to say, well, this is an inequality, so it's a little bit different. I need to actually think about where would these inputs be positive. And to me, the easiest way to think about this is a graph. Especially since this is a parabola, it's an easy one to think about the graph. I know that this parabola is going to open up because this is a positive 2. There's no negative out front. And I know the x-intercepts. The x-intercepts are positive 3/2 and negative 2. So if I just sketch that real quick, negative 2, positive 3/2. Here's my parabola, very rough, very wiggly. Sorry about the stylus. So where is this parabola positive? Where are the outputs positive? Well, they're positive here and here. So that's when x is less than negative 2, because we're going to the left of this negative 2. We're going to the left of this negative 2 to get these positive values, and to the right of the positive 3/2. So that tells me that my answer is x is less than negative 2 and x is greater than positive 3/2. This skill is actually going to be super important in calculus. We're very, very frequently wanting to know on what intervals is some polynomial function or even rational function or even exponential function positive or negative. Just any function, we want to break it up and say it's positive on this interval, it's negative on this interval. And by interval, I mean greater than 3/2. This interval from x equals 3/2, greater than that, all the way to positive infinity, this thing would be positive. From x is negative 2 all the way to negative infinity, my graph's outputs would be negative, or sorry, would be positive. And then in between the two values, from negative 2 to positive 3/2, my outputs would be negative. Last question, very exciting, we're almost done here. Just evaluating a piecewise function at a couple different points. We plug in negative 4. Nothing special actually happens at negative 4. It's just right here. Appears to be negative 3. At negative 2, though, we have this jump, so just make sure you recognize this is the one that is filled in. This is an open circle, so that's not the actual function value, so it's negative 1. And f of 4, again, filled in circle, actual function value, open circle, not the function value, so it's positive 1. Okay.